All right, so let's talk about classifications. Classifications of stability. We've seen examples of each of the kind of stability for real eigenvalues, and that's what we're going to talk about first, and then we'll get to the complex stuff after that. So, first situation, if both eigenvalues, which we're going to call lambda, when someone says lambda, you should think, oh, they mean an eigenvalue. If both eigenvalues are positive, then we have a situation like this. I didn't leave myself nearly enough room. So I'm going to draw the things that I'm going to refer to as the eigenlines here. And I'm just going to draw them kind of generically. So we're going to have two eigenlines. Maybe they look something like this. And when your eigenvalues are positive, it means your eigenlines point away from the origin. As I was, where'd you go? I had the piece of paper here. Yeah. Sorry, I had 1 second. Give me 1 second. I had something I wanted to say. Yeah. So something I want to point out or tell you is that the eigenlines represent the strongest lines of attraction or repulsion. So on the eigenline, that's where you are directly pointing towards or away from the origin. Whereas starting at some other initial condition, it's not a perfect direct away or towards the origin. Like, for example, if we're starting, say, like right here with some initial condition, watch for a second. We're not going to be pointing that way. We're not pointing directly out from the origin. We're getting pushed away this way and that way. So we're kind of doing something maybe like that. That's what's happening. So if both eigenvalues are positive, the equilibrium, which is always going to be 0, 0 for these linear systems of differential equations. Later on, if we talk about nonlinear ones, you can have other equilibria. The equilibrium is called an unstable node, or a source. Okay. If both eigenvalues are negative, I should let myself more. I feel like I'm using up my paper in the least efficient way possible. That's all right. If both eigenvalues are negative, then we have a similar sort of situation. So now along the eigenlines, which again might not point in exactly these directions, right? They could be in whatever directions the eigenvectors happen to be. I'm just kind of drawing them generically. But now along the eigenlines, we're going to be pointing inward because our eigenvalues are negative. Then the equilibrium, still 0, 0, is a stable node, also called a sink. I kind of think of it like a drain. Like here, all the water is draining into the hole, whereas the source, it's kind of like all the water is coming out of the faucet. And then thirdly, if you have an eigenvalue of each sign, so if one of your eigenvalues is positive and the other one is negative, the equilibrium is a saddle. There is no other fun name for saddle. It's just a saddle. And so this situation looks kind of like this. Oh, and I should point out, sorry, back to the previous example for a second. Here, if you have some initial condition like this, you're going to get pushed inward towards the origin because both these are pushing you downwards. And then thirdly here, if we have this situation where one of your eigenlines, you're pushing away from the origin, and on the other eigenline, you're pushing in towards the origin, then we have a saddle. And so if you start somewhere like here, you're going to get pushed kind of towards the origin for a moment, but then the other one's going to take over and push you away. And often for this one, you kind of draw an initial condition in all four kind of quadrants of your eigenlines. You can see like, oh yeah, this kind of deal happens, this kind of deal happens, this kind of deal happens. I kind of think of it as like literally on a saddle, like you're going in towards the equilibrium in one direction, but then if you fall off to the side, you're going to go away. That kind of makes sense. Like if you think about an actual saddle that you would put on a horse, if you start like up here at the high point of the saddle with like a little ball or something, you might roll down towards the middle of the saddle. But then if you're not along that perfect line where you're rolling down towards the middle, you're going to go off to the side. And so same thing here. If you're perfectly on this middle line here, you're going to go towards the origin. But if you happen to be off to the side just a little bit, you're going to get pushed away off the side of the saddle. It kind of works. It's not like a perfect analogy, but it's a not terrible analogy. Yeah. I will point out this is considered unstable. There is one direction of stability, but any other place you're starting at that isn't on this initial eigenline is going to be unstable. And so there's actually kind of a really fun way. I think it's fun. There are some fun ways of determining what sort of system you have based on your matrix. So let's look at 3 examples here, and then we'll talk about the complex stuff. So we're going to have the usual setup. If your equation x dot equal to a times x, and of course, A is a 2x2 matrix, as it usually is. We're going to analyze the stability of the equilibrium, 0, 0. Basically, is it a sink, is it a source, or is it a saddle? So let's say our first matrix is A equal to -4, 2, -5, 3. Okay. So there's a couple ways to go about this. Your job at the end of the day is to figure out not what values your eigenvalues are, but whether they're both positive, both negative, one of each, or if we're complex, if the real part's positive, the real part's negative, or the real part's 0. But again, we're not complex yet. So there's actually probably 2 or 3 good ways of doing this. Here's one way. Determinant of A minus lambda I. The usual way. We say that's equal to the determinant of -4 minus lambda, 2, -5, 3 minus lambda. If we do this, it's going to end up being, let's see, -4 minus lambda times 3 minus lambda minus 2 times -5. So I'm just going to write as -10. And simplifying this, that's going to be lambda squared. Minus 3 lambda plus 4 lambda is plus lambda. Minus 12 plus 10 is -2. And we're going to set that equal to 0. It does factor. They don't always factor. A lot of the times they'll factor, but sometimes they don't. We get lambda plus 2 times lambda minus 1 equal to 0. So I'm getting lambda equal to -2 and lambda equal to +1. So that means that the equilibrium 0, 0 is what kind of thing? Is a saddle. Okay. We're going to look at this next one in a slightly different way. So let's say the next matrix is 6, -4, -3, 5. So there's another way of determining whether your eigenvalue, what your eigenvalues are. It's really the same, it's just another way of looking at it. So instead of doing this calculation here, check this out for a second. We're going to find the determinant of just A. which people often call capital delta. And that's going to be equal to 6 times 5 minus -4 times -3, which is 30 minus 12, which is 18. And then we're also going to find the trace of A, which people often call tau. The trace of a matrix, of any square matrix, is just the sum of all the diagonal entries. So that's going to be equal to 6 plus 5, which is 11. And then the way we're going to find the eigenvalues is by using essentially the quadratic formula. Let me show you. So we're going to say that the eigenvalues are equal to, I have to remember how, I always forget if it's the negative trace or the positive trace. It's going to be the trace, yeah. It's going to be the trace plus or minus the square root of the trace squared minus 4 times delta all over 2. Sometimes I will say, I don't know if I agree with the statement, but sometimes doing it this way feels easier. So in this case, we're going to get the trace, which is 11 plus or minus the square root of 11 squared minus 4 times 18 all over 2. Here's the thing we want to focus in on. I don't really want to know what this number is, although we're probably going to find it. What I really want to know is, are both of those numbers positive? Or are both of those numbers negative? Or do I have one of each? Well, certainly, at least one of them is positive. 11 plus whatever over here is going to be positive. So the real question is 11 minus this also going to be positive, or is it going to be negative? So is this thing here bigger than 11 or smaller than 11? Let's see, 11 squared minus something is smaller than 11 squared, right? Whatever's inside of here is smaller than 121. And if you take the square root of a number that's smaller than 121, it ends up being smaller than 11. So since this inside part here is less than the square root, less than 11 squared, this whole thing here is going to be 11 minus a number that is smaller than it. And so what it's going to be giving us is going to be 2 positive eigenvalues. Now, let's actually find them just to see it. But that's one way you can do it. So it's going to be 11 plus or minus the square root of 121 minus, let's see, 4 times 18 is 72. And then 121 minus 72 is 21 plus 28, which is 49. So you have 11 plus or minus the square root of 49 all over 2, which is 11 plus or minus 7 all over 2, which is 18 over 2, or 4 over 2. So there are your actual 2 positive eigenvalues. The reason I point this, well, let's do another one, and then we'll talk a little bit more on this. Sometimes people has a little bit of words. Has he mentioned this formula at all? Okay. All right. Right. Because sometimes you do it. Well, then that shows you when you have like a spiral. So we'll do one more with this, and then we'll kind of talk about when you may or may not want to actually use it. Let's look at the next example here, which is going to be A equal to the matrix 0, -2, -1, 3. So let's find the determinant and the trace of A. So the determinant of A, delta, is 0 times 3 minus -2 times -1, which is -2. Fun fact, I know for sure I'm going to have a saddle. And I'll show you why. So let's find the trace. The trace is equal to 0 plus 3. Just 3. And using this formula, by the way, the place this formula really comes from, just so you all know, is I'm really just, let's actually look back at our first example for a second. This first example here, this equation right here is lambda squared minus the trace times lambda plus the determinant. Right? The trace of this matrix is -4 plus 3, which is -1. And that's a minus minus 1 to give you a +1 there. And the determinant is -12 minus -10, which is -2. And so what you're really doing is you're taking this equation and then throwing the quadratic formula at it. You're saying, oh, my A is 1, my B is negative the trace, and my C is delta. And so then my formula is my trace, my negative trace, plus or minus the square root of my trace, my negative trace squared. But if you have a negative square, it comes out positive, so we don't really care. And then minus 4 times A times C, all over 2 times A. So really, we're just using the same formula that we could have done a different way. But here's what I want you to see in this next part. I promise you, it might be worth it. With an easy promise to keep, it might be worth it. So here's what's happening here. If I use this formula to find my eigenvalues, it's going to be the trace, let's write it again, plus or minus the square root of your trace squared minus 4 times delta, all over 2. Now check this out. It's going to be 3 plus or minus the square root of 3 squared minus 4 times -2, all over 2. And I know for sure, because my determinant was negative, because this delta was negative, because I have a negative right there, this whole equation is going to give me one positive value and one negative value. And here's why. 3 squared plus a number, plus 8 in this case, is bigger than 3 squared. It's bigger than 9. So the square root of this is bigger than 3. The square root of 9 plus something is bigger than the square root of 9. So since this is bigger than 3, let's pretend it's 4 for a second. 3 plus 4 is positive. 3 minus 4 is negative. 3 plus a number bigger than itself is positive. 3 minus a number bigger than itself is negative. If this was a -3, it would still work. -3 plus a number bigger than itself is positive. -3 minus a number bigger than itself is negative. So if this thing gets bigger, if delta is negative, you will always get a saddle. So one quick thing you can do when you're looking at just classifying is, if you can easily see that the determinant of your original matrix is a negative value, you can be like saddle all day long and you're done. So here we're getting 3 plus or minus the square root of 17 all over 2. And then 3 plus root 17 is positive. And 3 minus root 17 over 2 is negative. So we have a saddle. Do one more and then we'll talk about the complex stuff. Let's say my matrix was this. So what I'll really say here is you can do this either way. You can either do it the way we've been doing it, which is probably easier at this juncture because we're used to doing it that way, or you can try doing this new thing. There is more to say about this new thing, which is why I don't want to leave it in the dust. But I'll try not to use it all the time because I do think doing it both ways is good. So determinant of A minus lambda I is going to be determinant of -3 minus lambda, -1, 1, -6 minus lambda. Multiply it out. We've got the determinant. Sorry, not that I'm not going to write the determinant. I'm actually going to multiply it out. We're going to have -3 minus lambda times -6 minus lambda minus 1 times 1. 0, let's see. Lambda squared, and then I have a +6 lambda plus 3 lambda is +9 lambda. I have a -6 times -3, which is +18, and then +1 is +19. Okay. So then quadratic formula. So it's going to be, right? Because it's quadratic formula because we can't factor this, right? You can't multiply the 19 and add it to 9. At least not with integers. So lambda is going to be -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. I'll point out, this is exactly the same formula we would have had if we'd done it this way. Our trace is -9. Our determinant is 18 minus 1, which is 19. Right here, I scratched it out because I made a mistake. It says, don't look at that. All right, so I'll just point out here, the trace of this matrix is -3 plus -6, which is -9, and the determinant is -3 times -6 minus -1 times 1, which is positive 19. So you're exactly getting the trace plus or minus the square root of the trace squared minus 4 times your determinant all over 2. It's really the same formula. It's just we don't always use the quadratic formula because a lot of the time things factor, which is lovely. We love it when it factors. And then if we simplify this, I've got -9 plus or minus the square root of, let's see, 9 squared minus this, hopefully. So if this was going to be negative inside here, then I would have to start talking about spirals. It's barely positive. 9 squared is 81. 4 times 19 is 4 less than 4 times 20, which is 4 less than 80, which is 76. So I'm getting -9 plus or minus the square root of 5 all over 2. And either way, -9 minus root 5 is certainly negative. -9 plus root 5 is also negative because root 5 is something around 2 point something. So this is both negative. Lambda 1 and lambda 2 are both negative. So we have a what? Stable node or a sink, either way you want to call it. Cool. All right, let's talk about things that are complex. Actually, I should say, are there questions about anything I've said so far before we move on to talking about things that are complex? Other than right down there. So this says here that my eigenvalues are equal to -9 plus or minus root 5 over 2. And then I wrote lambda 1 comma lambda 2 less than 0, which means they're both negative. And when both eigenvalues are negative, we call that a sink or a stable node. You are welcome. So the -9 came from, so right here, I'm using the quadratic formula. I'm saying, okay, my A is 1, my B is 9, my C is 19. And then the quadratic formula is -b plus or minus the square root of b squared minus 4ac all over 2 times a. Right? There's my -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And I'll just point out, because it is true, in this formula up here, I'm technically ignoring the sign of b right there when I square it because it doesn't matter when I square it. So it's okay to write tau here or negative tau and you'll still get the same result. But people are lazy and don't want to write negative tau quantity squared, and we don't. Okay. Let's talk about complex eigenvalues. Think of that song. You guys are like, what song about complex eigenvalues? No, not that song. Okay. Anyway, so what's a complex number? With I, what is I? Right. I is the square root of -1. And there's nothing else to say about it, really. I mean, there's a lot to say about it. I squared is the square root of -1 times the square root of -1, which is going to be -1. I cubed is I squared times I, which is -1 times this times I, which is -I. And I to the 4th is I squared times I squared, which is -1 times -1, which is 1. And then the pattern repeats. I to the 5th is I to the 4th times I, which is just 1 times I. And I to the 6th is I squared, and so on and so on and so on. It kind of feels similar-ish to how the derivatives of sine and cosine repeat after 4 iterations. Derivative of sine is cosine, derivative of cosine is sine, negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is positive sine. You do something 4 times, you get back to where you started. You multiply by I 4 times, you get back to where you started. Kind of similar, but they are related, which is why I'm mentioning it. So what's a complex number? Complex number, we typically generally write as a plus or minus that. I don't want plus or minus really. I want a plus bi, where a is the real part. And that's the part that's going to determine whether we have stability or instability in our system. And people, I feel like there's not a lot of great agreement here. I feel that, oh God, can I say words? People usually say that B is the imaginary part. B is the imaginary part. But some people might say it's B times I. So like, for example, if my number was 3 plus 2i, I would say the real part is 3. Now, I probably would say it the other way. And the imaginary part is 2i. That's the way I would say it. So I would say B times I is the imaginary part. But either way is correct. People use different words to say the same thing all the time. Or for example, if my eigenvalue was equal to, say, 4 minus 5i, watch this for a second, then the real part of lambda is equal to 4, and the imaginary part of lambda is equal to negative 5i. That is often, not always, but often notation that gets used to distinguish between the real and the imaginary part. Okay. Good news. When we talk about eigenvalues and they're complex, they they always come in conjugate pairs. Meaning we get eigenvalues like 6 plus or minus 2i. Or negative 4 plus or minus I. There's always going to be a real part plus or minus the same imaginary part. So that's going to be your 2 eigenvalues. 4 plus 2i and 4 minus 2i. Or negative 4 plus I and negative 4 minus I. I said 4, I wrote 6, I said 4, sorry. 6 plus 2i, 6 plus 2i. They're always going to come in pairs like this because they're always coming from the quadratic formula. We get that plus or minus situation happening. How much do I want to say about this? Did you talk about? Oh, okay, go ahead. So literally that. Well, I would say that those are two different things. So an imaginary number we have defined to be as I. So it's kind of like how back in the day people didn't think negative numbers existed. They do exist. They're a thing that we use in useful ways, even though they represent like a balance ode, maybe. Imaginary numbers, similar context. You're right, they're not real numbers, but they are still a thing that exists. A concept, exactly. Yes, thank you. They are a concept that has validity because they are useful. They are used in all sorts of interesting ways to make actual real things work, and real things work in the real world. That's a great question that I don't have great answers to.
Super advanced stuff, like I don't know how to
I mean,
surgery, but or
maybe like in chip technology. And again, I'm unfortunately never the right person to really ask you like what applications is this specifically useful in. Yeah, I'm sorry I don't have a better answer to your question.
The argument where it's like this versus like negative numbers, but negative numbers can be more easily like debuted against because of the bank accounts.
Right, exactly.
Just like
right.
And you can't, I don't know how you plot,
Right. So the way we plot imaginary numbers is by making the x-axis the axis for real numbers and the y-axis the axis for the imaginary part. So interestingly, the set consisting of all complex numbers, you could map in the two-dimensional plane.
but not 3D because then you have lines.
Well, I'm not saying not, I'm not saying you wouldn't need 3D. So just to kind of go with this idea for one more minute here. If I was just going to talk about real numbers for a second. So real numbers, which we often write like this, fancy R. There's lots of real numbers, negative and positive. Right? We've got 0, 1, 2, pi, -1, -√2, right? Anything that's real. There's no other way to say it. It's a number that is real. Right? Like, I don't know how to say it a different way. You can't. No, I mean, really, now you're like, I don't want to get too in the weeds here, like about what the definition of a real number actually is, because it's a little complex. No, it's not.
Not -1.
Right.
Or it's not the square root of -1.
Right. So real numbers are real numbers, which I know is not excellent. I wasn't planning on going down this way, so I was like, oh, now I have to think about what a real number actually is. Yeah. So great. And you can so what makes real numbers special, or kind of what kind of defines them, or is a defining feature, is that there's a well ordering. For any two real numbers, one of them, if they're not equal, one of them is always bigger than the other one. It's not true for complex numbers. There's not a well ordering for complex numbers. You can't say this complex number is strictly bigger than this one, or strictly smaller than this one.
Because when I still have the same value multiplied by anything else.
Right, but the thing is, like, you can have two different complex numbers that have the same sort of magnitude. So for example,
Like it's a vector.
exactly. So on this plane, I'll try and plot some points here. So this point here, 2 plus 2i is going 2 in the real direction and 2 in the imaginary direction. This is the real axis. This is the imaginary numbers times the real axis. So on this side, we have, 1, 2, 3, etc. -1, -2, -3, etc. On this other axis, we have I, 2i, 3i, down here, -i, -2i, -3i. And so in this complex plane, you could plot any real number. Or sorry, any complex number. Just like in this one-dimensional real number line, you could plot any real number. So and here you can see that once I place two numbers, one of them is clearly left of the other one, so one of them is clearly smaller than the other one. Where here, if I put a number here and a number there, you can't really talk about one of them being bigger than the other. You can talk about one of them having a larger magnitude or being further away from the origin. That's not the same thing as one just being strictly larger than the other. And I know it's not like a super great way of defining it, but it's enough to kind of see an important difference.
That makes sense. Vectors aren't inherently larger than another.
Right.
Okay.
Okay, so complex numbers. Where was I? Oh yeah. So there is a really cool formula involving complex numbers called Euler's formula. Although you might pronounce it incorrectly as Euler, but it's not, it's Euler. I used to pronounce it incorrectly for a long time. And then someone's like, it's Euler. I'm like, really? I'm like, yeah. So Euler's formula says the following. It says that e to the power of I times an angle is equal to cosine of that angle plus I times sine of that angle. It's probably one of the most well-known formulas in the world, actually. And it gives rise to one of the most well-known formulas as well, which is that e to the I times pi is equal to cosine of pi plus I times sine of pi. But cosine of pi is -1 and sine of pi is 0. People often write this as e to the I times pi equals 0 minus 1. It's famous because it includes 5 of the most important constants in math. E, I, pi, 0, and 1. But what are we going to use this for? So yeah, we do really need to say this. I really want to give you all the context. It's kind of a bit much, but we're going to do it anyway. So let's do this next problem. So we're going to classify the stability of the equilibrium 0, 0 for the following system of differential equations. X1 dot equal to negative x1 plus 2x2, and I don't know, I didn't mean to put a little vectory thing there, sorry. And x2 dot equal to negative 3x1 minus x2. And we'll have some initial conditions as well. X1 of 0 is equal to 2, and x2 of 0 is equal to 0. So here's our matrix. A is going to be negative 1, 2, negative 3, negative 1. Let's solve the, by the way, when you solve this determinant of A minus lambda I equal to 0, what you're solving is called the characteristic equation. Not that we need to know that, but it is what it's called. So that's going to be the determinant of negative 1 minus lambda, 2, negative 3, negative 1 minus lambda, 0. That's going to be, now look here just real quickly. I'm going to get negative 1 minus lambda times negative 1 minus lambda. Let's write negative 1 minus lambda squared minus 2 times negative 3. Okay, watch this for a second. I have negative 1 minus lambda squared, which, by the way, is always positive, right? Something, or I should say always non-negative, right? It's always bigger than or equal to 0, plus 6 equal to 0. That's not going to have any real solutions. There isn't a real number that when I do negative 1 minus a real number and then square it, I get negative 6, which is what I would need to get for this to be true. That means my answers are going to have to be complex. So what I'm trying to avoid doing here is I'm trying to avoid using the quadratic formula. What I'm going to do instead is I'm actually just going to bring that negative 6 over to the other side. So I'm going to say that negative 1 minus lambda squared is equal to negative 6. I'm going to take the square root of both sides. So negative 1 minus lambda is equal to plus or minus the square root of negative 6, which I'm going to immediately rewrite as plus or minus I times the square root of 6. Because the square root of negative 6 is equal to the square root of negative 1 times the square root of 6, which is I times root 6. And then finally, solving for lambda here, if negative 1 minus lambda equals plus or minus I root 6, then if I add that over here, add that over there, negative 1 plus or minus I root 6 is equal to lambda. So my eigenvalues are lambda 1 equal to negative 1 plus I root 6, and lambda 2 equal to negative 1 minus I root 6. And these are what we call complex conjugate pairs. These two numbers are conjugates of each other, but specifically they are complex conjugates. Because one is a complex number and the other one is the complex conjugate number. The complex part changes signs from positive to negative or negative to positive. Okay, that's funny. So the Grant, in case you didn't know, I often look at Grant's notes to teach this class. Like it's just a good source. Grant wrote, to actually write the solution with complex eigenvalues is complex. It is complicated. I don't know if he's going to have you do it or not. We will definitely go over the process if we have to do it in class. But if we don't have to do it, we shouldn't spend time doing it because it is terrible, to be honest. It's a real kind of bear. But here's the idea. Just like before, we're going to say that the general solution is your vector equal to C1 e to the lambda 1t times V1 plus C2 e to the lambda 2t times V2. So remember, I'll remind you all, the general solution to x dot equal to a times x is x equal to c1e to the lambda 1t times the first eigenvector plus c2e to the lambda 2t times the second eigenvector. That's your general solution. And it's true whether or not your eigenvalues are real or complex. So we're not going to find the eigenvectors because it sucks, unless we have to. But if we just think about this for a second, our general solution here looks something like, how can I write the words? X of t is equal to c1e to the lambda 1, which is -1 plus I root 6 times t, times whatever my first eigenvector is, plus c2 times e to the -1 plus, sorry, minus I root 6 times t, times whatever my second eigenvector is. Okay, here's what I want you to focus in on for a second. So we're going to focus in on the e to the -1 plus I root 6 times t. So check this out. I'm going to write this as e to the -t plus t times I times root 6. Sorry, my t's look like plus signs. Trying to make that look different. And then we're going to break this up as e to the -t times e to the I times t root 6. And then we're going to use that Euler's formula that I just talked about. E to the I times something is cosine of the something plus I times sine of the something. So this is equal to e to the -t times cosine of t times root 6 plus I times sine of t times root 6. So let me ask you all for a real quick second. I don't remember because it's been so long, but in 17A, did you guys talk about Taylor series at all for a minute? B? Yeah. So this formula, this e to the I times something equal to cosine of something plus I times sine of something, really actually comes from a Taylor's formula. I can show you, if I feel like people are like, this seems just kind of crazy what you're doing. Let me show you real quick, because we only have 5 minutes. Let me show you real quick where that's coming from, just so you all can maybe believe me a little bit more. So here's a couple things. I'll remind you of 3 Taylor formulas that you may or may not have seen, but here they are anyway. Maybe you want to see them though. So one Taylor formula is that sine of theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, etc. Sine of theta, you get all the odd powers. Or you could use x or whatever letter you like. I'm using theta because it feels good. Cosine of theta is all the even powers. 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus plus alternating signs every term. And then finally, e to the theta is all the terms and they don't alternate. It's 1 plus theta squared over 2 factorial plus theta cubed over 3 factorial plus theta to the 4th over 4 factorial, and so on and so on and so on. Okay, now here's the fun part. E to the I times theta. I'm going to replace every theta with an I times theta. So watch this. You get 1 plus I times theta plus I times theta squared over 2 factorial plus I times theta cubed over 3 factorial plus I times theta to the 4th over 4 factorial, and so on and so on and so on. Anyone remember what I squared is? No. -1. So I got 1 plus I times theta minus 1 times theta squared over 2 factorial. I cubed is minus I times theta cubed over 3 factorial. I to the 4th is plus 1. And this pattern continues. and we get another plus I times theta to the 5th over 5 factorial minus theta to the 6th over 6 factorial minus I times theta to the 7th over 7 factorial plus theta to the 8th over 8 factorial, and so on and so on and so on. And then if I group the I terms together and the not I terms together, look what I get. So the not I terms, 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. Oh, geez, that looks like cosine. It is cosine. If I group the I terms together and I factor out the I, I've got theta. I've got minus theta cubed over 3 factorial. I think you can see where I'm going with this. Plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial. That's exactly the sine of theta. So this really, really, really does truly equal cosine of theta plus I times sine of theta. Kind of cool. I think it's really cool. I'm not gonna say it's pretty cool. So back to what we're doing over here. We're then going to say, well, this is doing its thing. And what this means for us is that this part here is just going to cause oscillation. As this angle goes through a cycle from 0 to 2 pi, we're going to cycle through the unit circle. And so as time goes on and on and on and on and on, two things happen. One, this e to the negative t gets closer and closer and closer and closer to 0 as time goes on and on and on. Whereas this part here, you get cycling as time goes on and on and on. Or if you prefer, I probably prefer, or oscillating. I know we're just about out of time here, so let me give you the sum up here because I do want you to see this final part. So what this means for us is that your x1 as a function of time is getting smaller and smaller and smaller because e to the negative t is going to 0, but it's doing it in an oscillatory sort of way. And similarly, as time goes on and on and on and on, x2 does the same sort of deal. It flattens out kind of. And so then what's happening here is that for our actual direction field, if we're starting at the point, and I think it was 2, 0, x1 was 2, and x2 was 0. We start at the point 2, 0, and let time go on and on and on. Well, the x1 values get smaller and then larger, and then smaller and larger, and the x2 values get smaller and then larger. So we kind of do this spiraling because even though we're getting smaller and smaller and smaller, they're still going back and forth between positive, negative, positive, negative. So that's kind of what's happening there. And I might have gotten the direction of the spiral incorrect because it looks like, right, that is the incorrect direction because my x2 value should have started getting negative first, not positive. So not this. It should have been instead more like this. Spiraling inwards towards the origin. And we know it's a stable spiral because the real part of our eigenvalue was negative, which gave you the e to the negative t, which got closer and closer to 0 as time went on and on and on. If my real part had been positive, like our eigenvalue had been 6 plus or minus the square root of -7, then we would have an e to the positive 6t, and this part would have gotten larger and larger and larger while this part oscillated, and we would have spiraled outward instead of spiraling inward, and we'd have an unstable spiral. Yeah.
Is that the equation for the Fibonacci sequence?
No, not really. But I can see the connection you're making there, and you know what? Actually, there could be some relationship between Euler's formula and the Fibonacci sequence, but I don't. I don't know. I don't know the answer. Really, it's the real answer. All right, we'll talk more about spirals on Friday. But just know that just like with the nodes, if the real part is positive, you have instability. If the real part is negative, you have stability. And that's true whether your eigenvalues are actually real, and so you're just saying they're positive and negative, versus your eigenvalues are complex, where you're saying the real part is positive or the real part is negative. And then if you have one of each, it's a saddle.
Real and it's positive equals stable.
Unstable.
Unstable.
Positivity is instability because you're growing to infinity as time goes on and on and on. Because you're welcome, you have an e to the positive number times t. That's what you should really think of when you're thinking about stability versus instability, is if it's a positive eigenvalue, you have, like, if your eigenvalue is 5, you have e to the 5t, and that's growing bigger and bigger and bigger. If your eigenvalue is -5, you have e to the -5t, and that's growing smaller and smaller and smaller.